Today we are talking about Pauli's exclusion principle. Pauli's exclusion principle was given by an Austrian physicist named as Wolfgang Pauli in the year 1925. Later on, Wolfgang Pauli was awarded by Nobel Prize in the year 1945 for the discovery of Pauli's exclusion principle. So now a question arises, why we are doing Pauli's exclusion principle in our today's lecture? Because Pauli's exclusion principle is very important and it helps to explain a wide variety of physical phenomena such as the shell structure of an atom and the way how atoms share electrons. Moreover, periodic table can also be defined with the help of this principle. This principle is not restricted to just chemistry. This principle is a fundamental principle in the quantum physics also. So it's also very important in the quantum physics, and moreover it also plays a vital role in astrophysics. The Pauli's exclusion principle basically helps us to understand the electron arrangements in an atom and molecules, that how the electrons are arranged there. Say for example, it helps us in electronic configuration, and it also gives an explanation for the classification of elements in the periodic table. Here you can see what the Pauli's exclusion principle is. The Pauli's exclusion principle states that in a single atom, no two electrons will have an identical set or the same quantum numbers. Here we have four quantum numbers. N is the principal quantum number, L is the azimuthal quantum number, ML is the magnetic quantum number, and MS is the spin quantum number. From all these four quantum numbers, any of three can be same, but one is always different. So this is what described by Pauli's exclusion principle, and moreover it also says that no two electrons in the same orbital can have same spin. There are two silent rules that the Pauli's exclusion principle follows. The first one is again, no two electrons in the same atom can have identical values for all four of their quantum numbers. Which are four quantum numbers? Principal quantum number, spin quantum number, magnetic quantum number, and azimuthal quantum number. In other words, no more than two electrons can occupy the same orbital. Two electrons in the same orbital must have the opposite spins. Here, this is an atom of oxygen, and this is the electronic configuration of oxygen. Here in 1s we have 2 electrons, in 2s we have 2 electrons, and in 2p we have 4 electrons. So in the 2px we have 2 electrons. Now these 2 electrons have opposite spin, this electron and this electron. Now let's talk about spin quantum number for these 2 electrons. Spin quantum number is represented by ms. The spin quantum number for the electron with the upward direction is positive 1 by 2, and the spin quantum number for the electron with the downward direction is equal to negative 1 by 2. Say for example, all of the other three quantum numbers are same for these two electrons, still the spin quantum number is different. Here, this is what Pauli's exclusion principle states, that no two electrons in an atom have same set of four quantum numbers. Have a look at another example. It will help us to understand the Pauli's exclusion principle in a more better way. Here you can see fluorine atom. In the fluorine atom, 1s has 2 electrons, 2s has 2 electrons, and 2p have 5 electrons, as we can see here. So in the 2px we have 2 electrons, in the 2py we have 2 electrons, and in 2pz we have only 1 electron. In 2px we have 2 electrons, one with the upward direction and the other with the downward direction. Now, if you're just going to make a difference between these two, say for example, this is electron A, and say for example, this is electron B. Now, let's compare four quantum number for these two electrons. At first, we have principal quantum number. Principal quantum number is denoted by small n, and it tells us about the energy level. Because it belongs to shell number 2 is L shell. So we are going to write n is equal to 2 here because both are present in 2px. Then let's talk about the azimuthal quantum number. Azimuthal quantum number is represented by small l. For azimuthal quantum number, S is equal to 0, P is equal to 1, D is equal to 2, and F is equal to 3. Azimuthal quantum number for S is equal to 0, azimuthal quantum number for P is equal to 1, azimuthal quantum number for D is equal to 2, azimuthal quantum number for F is equal to 3 here. So here we can see we have 2px. It belongs to orbital P. So these two electrons belong to orbital P. So azimuthal quantum number for these two electrons is 1 here. So 1 here and 1 here. Then comes magnetic quantum number. Magnetic quantum number is represented by ml and ml here. So if we talk about magnetic quantum number is minus L, so on 0 and plus L. So what is L here? L is azimuthal quantum number. And azimuthal quantum number here for these two electrons is equal to 1. So minus 1 here, then comes 0, then come plus 1. So this is for X, this is for Y, and this is for Z. And here, these two electrons are present in 2px. So that's why the magnetic quantum number for this X is equal to minus 1 here. And for this electron is also minus 1. Now we are left with just spin quantum number. Spin quantum number is represented by ms. Now here we have two electrons, one with the upward direction and the other with the downward direction. The electron with the upward direction have spin quantum number 1 by 2, and the one with the downward direction has minus 1 by 2 spin quantum number. Now it's time to compare the 4 quantum number for electron A and electron B. So now the principal quantum number for electron A is equal to 2. And for electron B, it's also 2. So it's same. The azimuthal quantum number for electron A is equal to 1. And the azimuthal quantum number for electron B is equal to 1. It's again same. The magnetic quantum number for electron A is minus 1. And the magnetic quantum number for electron B is also minus 1. So 3 of them are exactly same. Now let's talk about the fourth one. The spin quantum number for electron A is equal to plus 1 by 2, and the spin quantum number for electron B is equal to minus 1 by 2. So here you can see the difference. In all of these 4 quantum number, 3 of them are same and 1 is entirely different. So this is what Pauli's exclusion principle says, that no two electrons in an atom have same set of 4 quantum number. The second rule for Pauli's exclusion principle was, in an orbital, the electron always have a opposite spin. And why this is so? We know electrons are a charged species. They have a negative charge. Moreover, electrons just not revolve around the nucleus. They have a spin around their own axis also. Thus, as a result, due to their motion, they create a magnetic field there. Two electrons present in the same orbital have opposite spin clockwise and anti-clockwise to cancel out the magnetic field generated by the other electron. This is the reason that in electronic configuration, whenever we fill 2 electrons in an orbital, we always fill it with opposite spin. Now, let's conclude our today's lesson. According to Pauli's exclusion principle, no 2 electrons in an atom have same set of 4 quantum numbers. And we have seen this with the help of an example also. If 3 of them are same, one should be different. This is what Pauli's exclusion principle says. On the other hand, Pauli's exclusion principle says in an orbital, no 2 electrons can have the same spin. It's even not possible. They should have an opposite spin. If one electron is with clockwise direction, the other should be with the anti-clockwise direction. So this is all about our today's lecture. If you like this lecture, please subscribe to this channel as it motivates me to make more such videos for you. Thank you very much.